Okay, thank you very much. My name is Denis Didier Rousseau. I'm president of the Climate Past, Present and Future Division, and I welcome you to this first union session. So as you can read on this first slide, our planet Earth is under increasing pressure. This union session will consider the broad geoscience aspects of those pressures by combining presentation of past variability in combination with present observation status and projection for the future of our planet. The past, present, and future will be addressed by the three keynote speakers which are on this slide. So we will start by Jim Tsakos, then we will have Eric Regnault, or Regnault in French, and we will finish by Michael Gill. So this session is planned as an EGU session, as a contribution to the ICSU, so International Council for Science Unions, ICSU meeting, which will be held in 2012 in London to prepare the 2012 Rio Summit. So this is the reason why I submitted EGU, the proposal that EGU must be present in this discussion and have a contribution through these three interesting talks. So I will not take the stage too long, and I will pass the presentation to Jim Tsakos.
Okay, first of all, I'd like to thank the organizers for the invitation to speak today. And when I was asked to talk on climate of the past, I realized the geologic record has many rich examples of climate response to changes in forcing, specifically greenhouse gas forcing. I can name many examples, glacial, interglacial cycles, to the extreme warmth of the Cretaceous. Obviously, I chose to speak on a topic that I'm most familiar with, the Paleocene-Eocene thermal maximum. So I apologize to those of you who work on other time intervals, other climate problems. I do think that all of these climate events of the past do provide us with some insight into the dynamics of the climate system. Before going on, I should also acknowledge the fact that what I have to talk about today obviously reflects the efforts of quite a few individuals, some of whom are listed here. So as a starting point, I always like to begin with our current situation, the rise in atmospheric CO2 over the recent past and then projected into the future 100 years. And these are projections from the coupled carbon cycle model comparison experiment. And obviously, CO2 levels will rise. The exact peak 100 years from now is a matter of debate. The differences in these models have to do with feedbacks in the carbon cycle, mainly the rate of sequestration by the ocean and biosphere. Nevertheless, it's likely that we'll see at least 2.5 to 3 times the pre-industrial CO2 levels, and with that we expect 2 to 3 degrees warming, depends on your sensitivity. As we move further into the future, what we'll see over the next 100,000 years, we can actually just use a more basic box model to look at the changes in the carbon cycle in CO2 and in climate. This particular model was designed by Richard Zabe at University of Hawaii, and we were using it specifically to simulate a carbon cycle perturbation in the past. And so in this simulation, it's the extreme emission scenario, 5,000 petagrams of carbon. A lot of people feel that we won't get there. We may be looking at 2,000 or 3,000 at most. But in the event that we were to go to this extreme, this is essentially the response we would see. The CO2 in the upper panel peaks at something around 1,800 ppm. And then you can see the gradual recovery, or at least initially a fairly rapid recovery, but a long-term gradual recovery that takes over 100,000 years. The main mechanism for sequestering that carbon is weathering of silicate rocks. The next panel shows the acidification of the ocean as that CO2 is absorbed by the ocean. We have this large drop in the surface ocean pH. Along with that, the saturation state drops as well, and then you can see the recovery. And I'll have more to say about this a little bit later. The third panel just shows the changes in the ratio of C13 to C12 in the Pacific Ocean, in the surface ocean, and in the deep ocean. And the point of this is simple, which is the anthropogenic carbon has a very distinct isotopic fingerprint, about -20 to -25 per mil. And so as this carbon is being taken up by the ocean, what we see is the immediate response in the upper ocean, which is where most of the anthropogenic carbon is accumulating. And we know that already the delta C13 of the surface ocean has dropped by about 1.5 per mil, and it will continue to drop at a very fast rate to about -4 or so. And then as the ocean mixes with the surface mixes with the deep, that signal will propagate into the deep ocean. And overall, we'll see about a 4 per mil negative excursion in delta C13. And finally, in the lowermost panel is simply a very rough estimate of the change in global surface temperature. This is not a climate model, it's a carbon cycle model. And all we did was simply take the PCO2, and then depending on which sensitivity you want to use, anywhere from, say, 1.5 to 4.5 degrees centigrade per doubling, we could see anything between about 2 to about 7, 8 degrees of warming with this CO2 pulse. And of course, there are issues about the sensitivity that are actually quite important and worth thinking about, especially from the geologic past. Now, this particular simulation, in some ways, has already been run. There's an event in the past that we know of, the PETM, which occurred about 55.6 million years ago. And what we understand about it in terms of climate is that we have global warming on the order of about 5 to 6 degrees centigrade, and I'll show you some of the records of that in a moment. We see evidence, very clear evidence, of a response in the hydrologic cycle, an intensification of the hydrologic cycle. And I think this is a key aspect of the event that I want to touch upon toward the end of my talk. And naturally, these impacts on climate and on the carbon cycle ultimately have impacts on the biosphere. And so that's a whole other story I won't have time to talk about. So let's go back in time. Here's a reconstruction of CO2 and in the upper panel and in the global climate as represented by this stack compilation of benthic fluoram oxygen isotope records. And the general pattern, of course, is that we have a period of higher CO2s during the Paleogene period when the climate is also warmer. And the details of this are changing all the time. I've just thrown up a couple of proxies here that represent mainly marine proxies, but they're terrestrial proxies as well, leaf stomata index, soil nodules, and so forth. And the bottom line is that all of them show higher CO2 through this period. And what's being debated now is just the magnitude or the absolute levels of CO2. in the climate record, this is fairly clean and straightforward. What we're seeing at the end of the Paleocene into the early Eocene is this long-term global warming trend. And then superposed on that is this transient global warming event, which is the PETM, which was only discovered 20 years ago, in 1991, by Kennett and Stock. So this is that event, and if you look at the changes in the ratio of C13 to C12 in the ocean, what we find is that during this period when we have the Paleocene thermal maximum, we see this negative excursion in the ratio of C13 to C12 in the ocean. And of course, this is one of the key pieces of evidence for a massive release of carbon. This carbon would be enriched in C12, much like fossil fuel carbon today. So in detail, if we begin to take a closer look at this carbon isotope excursion, this is what we know today. What you're looking at here in this lower panel is a carbon isotope record that came from ODP site 1262 in the South Atlantic. And this lower record is simply iron abundance record obtained by XRF core scanner on the same core. And of course, the iron content is reflecting the clay content, which is being diluted mainly by carbonate. This is a fairly long record, and as far as we know, it's stratigraphically continuous. It's the first record spanning this time interval. The sampling resolution is every 2,000 to 3,000 years, and so we can resolve all the orbital cycles. Westerhold and others have developed an astronomically tuned age model, tuning to the eccentricity curve of Lascar. And what we have now is a context, an orbital context for the PETM, all right? We can effectively match every one of these cycles to a change in the orbits. It turns out there are 400,000-year cycles in the C13 to C12 ratio. The minima tend to align with maxima and eccentricity. And that's true with all of these events, even some other hyperthermals or warming events later in the Eocene. The one exception is the PETM. It seems to be out of phase with this orbital pacing. And what this suggests is that there may be another trigger for the PETM other than orbital forcing. That's another story that I'm not going to get into today. So we have at least some good evidence now for the timing, the scale of the PETM. What makes it an interesting event from the perspective of climate dynamics is it's a very fast perturbation, a transient, right? And what we can assume is that all other boundary conditions are fixed, plate tectonics, things that we normally would worry about when we're looking over long time scales. The exception would be orbital forcing, as I just showed. We have a good grip now on the orbital configuration for this event. It's a very large signal, so signal-to-noise ratio is good, especially when you're trying to reconstruct climate or PCO2. Another interesting aspect of this event was that there was very little ice around prior to the excursion. So what we're looking at is a climatic response without ice feedbacks, which, again, from a climate dynamics perspective, this is an interesting experiment. The change in PCO2, this is sort of an Achilles heel in a sense for us working in the past, being able to reconstruct CO2 levels. But what we have here is a very rapid perturbation, which allows us to take a different strategy for reconstructing CO2 levels, which is we can use the information that we have about changes in the carbon chemistry of the ocean to effectively simulate or model the change in PCO2. So how do we do that? Here's another record of the PETM. These are benthic 4M isotope records, carbon isotopes and oxygen isotopes. And of course, you could see in the benthic 4M carbon isotope record, this 3 per mil, 3.5 per mil excursion. The oxygen isotopes just show the warming. And I should mention this is a very old record. It was actually put together in 2000. There are much more detailed records, but I like this one. It's fairly simple. The warming is about 5 degrees in the deep sea. It's fairly uniform throughout most of the deep sea. And then, of course, what you're looking at in the lower panel is the carbonate content of sediments at one location in the South Atlantic. And I'll show you a more detailed record of this in a moment. But what it is simply a dissolution horizon. There's a complete loss of carbonate at this particular site. We know this is a global dissolution horizon. And this is the evidence of ocean acidification. The degree of acidification we would expect to scale with the amount of CO2 that the ocean is absorbing, okay? So a large group of us came together many years ago and decided to try to use observational constraints along with models, 2 different classes of models to constrain the mass of carbon that was released during this event using the acidification pulse as one constraint. And so the 2 models, one is a simple box model, LASCAR, and then the other is a more sophisticated Earth system model, GENIE. And a number of experiments have already been run and published on, and I'll show you the data from those in a second. The main observational constraint that we have is this changes in the carbonate compensation depth, the degree of acidification of the ocean. We have carbon isotopes as well, which really can't be used to constrain the carbon input unless you know the exact source of the carbon. And as it turns out, we don't. There's a debate going on about where all this carbon came from. Now, the data that I'm going to show you, one record, or set of records, are from the Walvis Ridge in the South Atlantic. And this is this famous depth transect of cores that span the PE boundary from about well, these are paleo depths, about 1.5 kilometers to 3.5 kilometers water depth. And what we know is that the CCD shoaled past all those sites very quickly and then slowly recovered. And that's represented by this low carbonate layer in all 3 cores. We have other records like that from the other ocean basins, and using those observations, Richard has gone through, Richard Zaby has gone through, and he's simulated a carbon cycle pulse or a response to pulse of carbon with initially 3,000 gigatons over a couple thousand years, followed by a long-term additional input of about 1,500 gigatons, so a total of 4,500 gigatons. And what he's doing is he's trying to replicate the isotope excursion. He's assuming that the end member delta C13 is minus 50. These are observations. And then this is his reconstruction or his simulation of the CCD, calcium carbonate content in the Atlantic Ocean. Those are the observations. And so this is sort of a best fit, multiple simulations to try to replicate observations. As I said, the mass that he comes up with is 4,500 gigatons. The other aspect of this is simply the rate of the input. You can take 3,000 gigatons and run a simulation like this, where you just add it over 1,000 years versus 80,000 years. And what's important is that it's hard to get the CCD to shoal 2 kilometers unless you add the carbon very quickly. So this is potentially one constraint on both the mass and the rate. And then the impact on CO2 is quite variable depending on how fast you add that carbon, at least initially. Long term, it settles in at about the same level. Okay? So that's one simulation. I won't show you the details of the GENIE simulation. It's a very different model. And some of the starting parameters were a little different, for instance, the depth of the CCD. And in this model, in this simulation, set of simulations, they come up with a total carbon mass of about 6,800 gigatons. So you have these sort of 2 ranges, about 4,500, 6,800 gigatons. Okay, now quickly, I just want to show you the climatic response. What's the change in global temperature? We have various proxies, and I'm only going to show you a couple of records from key locations, the polar regions and one mid-latitude region, starting with the Bass River in New Jersey. And what you're looking at here is the carbon isotope excursion in organic matter. All right, this is a siliciplastic site. There are some 4Ms in there. And here are the oxygen isotope values of those 4Ms. These are individual shells of planktonic 4Ms. And what's interesting is that you see a change in temperature from about 25 to about 33 degrees or so. This is the TEX86 proxy, which gives about the same magnitude of warming and peaks at slightly higher temperatures. And so it's interesting to see these two different proxies from the same core. The planktonic formifer give you a sense of range or maybe seasonality in temperature. And TEX seems to be biased toward what are the warmest temperatures. So maybe it's telling us about summertime temperatures. That's certainly true when we go to higher latitudes for TEX. I'll show you in the next slide. This is just an old record published by Debbie Thomas. And it just shows planktonic 4M oxygen isotope ratios over here, pre-excursion to peak excursion. This site is off of Antarctica, so it's our Southern Ocean site. And the bottom line here is the temperature changes by about 8 degrees centigrade, just based on the oxygen isotopes. Peak temperatures might have been as high as 20 degrees centigrade. And then we have a site here in the Arctic, so the other pole on the Lomonosov Ridge. This is completely devoid of carbonate, so the only proxies you can use have to be organic base. And so here's a study where two temperature proxies are being measured. One is the TEX86, and it shows temperature rise of about 5 degrees centigrade with peak temperatures of around 22 degrees centigrade. It's probably summertime temperatures. What's mean annual temperatures? We don't know, but this is the best we can do. So now that we have at least 3 examples, I can show you where these sort of plot up relative to a simulation of the climate system using CCM. And in this particular simulation, Matt Huber ran this. What he's trying to do is he's trying to get his model to match the temperatures, especially at the poles, toward the poles, all right? And so he has to hike up the CO2 to about 4,500 ppm before he gets a match in temperatures. Those are the annual temperatures. You can do it for summertime temperatures in the northern hemisphere, and you might get a closer fit of getting temperatures around the margins of the Arctic into the 20s. But you can see it requires a lot of CO2. The problem that you also run into is that the tropics start to get very hot. There are places where you see temperatures in the 40s and beyond. And the question is whether there's any evidence to suggest that it got that hot in the tropics. There's a possibility that the CO2 levels were lower and something else was working to amplify polar temperatures. And this has been a problem that we've had for a long time, working back in the Paleogene and Cretaceous to try to understand why polar temperatures are so warm. And it's a problem that a couple of people at Harvard took on, Dorian Abbott and L.A. Zipperman. And basically, they came up with this idea of a high latitude convective cloud feedback, which I like. It's an interesting idea. They're thinking out of the box a bit. And it's a very simple thing with these convective clouds forming over an ice-free Arctic during the wintertime and effectively trapping heat there. And then they disappear in the summer, and you have plenty of heating. And in more sophisticated simulations, they've looked at GCM runs, and they think that some of the models actually replicate this feedback, this strong, potentially strong cloud feedback as an amplifier. How am I doing on time? Okay, so I can go right to the end of. So what we're looking at here is something like a global change in temperature of about 5 to 6 degrees centigrade. And with the current constraints that we have on the CO2, what we would estimate as its climate sensitivity with this particular event is something on the order of 3 to 5 degrees centigrade per doubling of CO2. So sort of more toward at the high end of estimates for climate sensitivity to CO2 forcing. And keep in mind, this is without an ice feedback, all right? So there's probably a feedback involved. Maybe it's vapor and clouds. But again, it's not an ice feedback. And then finally, as far as why the focus on vapor, there is a significant response in the hydrologic cycle. And we're just really starting to get a grip on what's happening. Some of the evidence is very direct. When it rains a lot and you get lots of erosion, that material gets transported into basins, into the shelf and the slope. And we see that globally in a lot of different places, which all of it seems to be occurring right at the onset of the PETM. And I'll just give one or two quick examples. This is a paper published in 2000, and it's an interesting section. You have this sequence of coastal plain sediments, very fine grain, and then right in the middle of the section is this conglomerate bed. And it's been there for a while. People have known about it for a while. But it was subsequently shown to occur right at the base of the PETM during the onset of the carbon isotope excursion. That's the conglomerate bed, all right? And so the interpretation is that at the onset of the PETM, during the initial phases of warming, there was much more erosion going on. And the indication is that these are high-energy flood events. So shift toward extreme seasonality of precipitation, or at least much larger storms with greater precipitation. And we see this in other sites in the northern hemisphere. This is a section in New Zealand, a PE boundary section. And the only thing here that you can really look is this record, which is the accumulation of siliciclastic sediments. And so you get this real sharp peak at the onset of the event. So there aren't many of these records at the moment, but there are enough around to suggest that we're getting some sort of increase in erosion, very much an intensification of the hydrologic cycle. But another way to think about it is that there's a shift in the delivery of precipitation, that you're starting to see more monsoon-like climate conditions, short, intense wet seasons, but maybe long, dry seasons. Okay? So that's it. These are my closing remarks. Very simply, I'm just going to say that I think that the sensitivity that we see during this period would be more consistent with the high-end estimates of climate sensitivity to greenhouse forcing. And obviously, the boundary conditions are different. That could influence sensitivity. There's no ice. Are there other greenhouse gases involved? We don't know. And then finally, maybe that feedback that enhances the sensitivity involves vapor and the hydrologic cycle. Thank you.
Okay, so we will keep questions for the roundtable. So we will pass to the next speaker, Eric Rignaud, who will speak about melting of the great ice sheets in Greenland and Antarctica.
Exactly what I was expecting. This is great. Thank you very much. Switch the slides. Eric. So, yeah. Then you come back.
I can speak on both. Thank you. I'm going to talk about melting of ice sheets in Greenland and Antarctica, and I'm going to show you some recent results of the mass balance estimation of these ice sheets, what we think is forcing the systems in terms of climate, examples of rapid changes in ice sheets and what they might mean for future evolution of ice sheets. And I'll show you also the impact of these results on sea level. The Antarctic ice sheet is about 14 million square kilometers, 50% bigger than the United States. Greenland is about 2 million square kilometers, 7 times lower. And the challenge of these studies is to estimate whether these vast extents of ice are shrinking or growing with time. And we know that they're not shrinking or growing at astounding rates because they're still there. So we know that the rates are small in terms of the volume contained in these ice sheets. Precipitation in Antarctica is very low, comparable to deserts. There's 60 meters of sea level equivalent stored in the ice sheet. And the annual turnover of ice in Antarctica is equivalent to 6 millimeter per year sea level rise. In Greenland, precipitation is a bit higher. There's 7 meter of sea level equivalent locked up on the island, and the annual turnover of mass is about 1.4 millimeter of sea level rise. Some terms I'm going to use here in the next few graphs are the surface mass balance and total mass balance. On an ice sheet, you have snow accumulating and densifying into ice and flowing to the coast under the action of gravity. And at the coast, it produces runoff, surface melt, it produces icebergs, and in a case where the glacier ice is able to survive on the ocean, it forms a floating ice shelf that interacts with the ocean and melts at the bottom. We usually distinguish the surface mass balance, which is the net accumulation of mass on the surface of the ice sheet, from the total mass balance, which includes the removal of ice at the periphery from calving of icebergs and melting of subglacial melting of floating ice shelves. These are the different techniques to measure ice sheet mass balance. The radar laser altimetry technique measures the changes in surface elevation of the ice sheet over time. So it measures volume changes, and it's been available for, from 92 with precision, from 92 to present. So the big uncertainty in this technique is to transform this volume change estimate into mass change estimates, because you don't know at which density these changes are taking place. The density of ice is 0.9, density of snow is 0.3. So depending on what's changing, you have a 50% uncertainty in the mass changes. But it provides an indication of areas going up or areas going down. Since 2002, we've been able to use results from term variable gravity from the GRACE mission, which operates at a much coarser resolution. We see details about 400 kilometers in size with this technique. The advantage is that it measures directly the changes in mass of the ice sheet, independent of density changes, independent of what's actually causing the changes, combined with the rebound of the crust associated with post-glacial rebound. And then the last technique is the mass budget method, which compares accumulation of mass in the interior with perimeter fluxes to determine the mass balance. So it involves a lot of measurements, and it's been available from 1992 to present using satellite data. So these are some results from altimetry. This is a map here of changes from aircraft campaigns by NASA, and this is the result of the ISAT-1 time series from 2003 to 2007. They show the same picture of a small increase in the interior regions over that time period, and an increase in thinning along the coast, manifested by these yellow to red areas. And you see that there's enhanced thinning along some special sectors, which correspond, as you see here in this map of ice velocity, to areas that are flowing fast, which are depicted here in blue and red. So a lot of the thinning ongoing at the coast is caused by the enhanced flow of ice towards the ocean. In Antarctica, the ISAT results published by Pritchard et al. Shows a similar picture. They excluded the interior because it's difficult to use this technique to say much about the interior. But you see coastal thinning in the West Antarctic basin here, Pine Island, Thwaites, and Smith. In this area, we see a thickening of the glaciers, which is not a climatic signal. It's associated with the changes in basal condition of these ice streams. And we also see some signs of activity in East Antarctica. This is Denman and Totem Glacier here and Cook Ice Shelf. And again, as in Greenland, these areas of most rapid thinning correspond to the areas that are flowing fast. So what we're seeing here is not a change in snowfall, it's a change in dynamics of the ice that's driving the system. When we look at the mass balance budget for the Antarctic ice sheet, so we compare the interior accumulation of snowfall from a regional atmospheric and climate model. This is in this case, the University of Utrecht model. And we compare that with estimations of mass fluxes around the periphery. So for that, you need to measure the velocity of the ice, how thick the ice is, and do this over the gateways by which the ice is pushed towards the ocean. We find something similar to what you saw in the picture before, a large mass loss from this sector here of West Antarctica, Pine Island, Thwaites Glacier. Mass loss in the northern tip of the peninsula where the ice shelves have collapsed and the glaciers are accelerated. And we see some tiny losses in East Antarctica. This is the marine-based part of East Antarctica, but it's compensated by some thickening in some other areas. Overall, if we look at those 10 years, we see an increase in mass loss in the Antarctic, and that's entirely from changes in glacier flow. In Greenland, this is a map of coastal velocities here with the red blotches corresponding to areas where glaciers sped up, and this was measured. You see that, and blue blotches correspond to areas that did not speed up. On this plot, we resolved on a monthly resolution the evolution of the total mass balance of the ice sheet into two components. The surface mass balance is represented by these circles here. You see a lot of fluctuations from year to year in surface mass balance, but a gradual decrease in the surface mass balance, which is caused entirely by the increase in runoff, increase in surface melt of the ice sheet. And the discharge has been increasing more steadily. You know, glaciers don't change speed so much seasonally, and they don't change speed so much from one year to the next, so you find a more regular curve, and also an increase here at 9 gigatons per year squared. Interestingly, the mass loss is partitioned about equally between an increase in melt and an increase in glacier flow in Greenland. Whereas in the Antarctic, since there's no runoff and there's no change in precipitation, it's entirely driven by the glacier flow. These are some results from GRACE. This is from the early part of the GRACE record, where you see a big blob of mass loss in southeast Greenland and a little bit of loss in northwest Greenland. In subsequent years, the loss in southeast Greenland has decreased a little bit, and the mass loss in northwest Greenland has increased. But overall, the ice sheet is losing more mass now than it was at the beginning of the GRACE mission. A similar picture emerges from the Antarctic ice sheet. A big blob of mass loss in the West Antarctic sector of Pine Island Bay and the Northern Peninsula, intensifying over time, and some indications of possible changes in East Antarctica as well. In this view graph, we put together the two techniques of mass budget and the GRACE data. A lot of results have been published over the last few years using these techniques separately, sometimes over different time periods, different processing schemes. We wanted to compare them and see how well they agree, and you see that the GRACE data here are plotted in terms of mass loss. Usually a lot of publications on GRACE plot the mass as a function of time, so this is the derivative. And there's a very good agreement over the common time period in Greenland and also in Antarctica on how the mass loss is changing with time. And you also see clearly that this mass loss is increasing with time. And it's about 22 gigatons per year square in Greenland, slightly less in Antarctica. You see that in Antarctica, the fluctuations in surface mass balance are much larger than in Greenland. And in fact, if you just use the 8 years of GRACE data, it's still not long enough to really determine the acceleration in ice sheet loss with great precision. We need at least 2 decades of observations to really extract this trend in the Antarctic. Well, this plot is the sum of Greenland and Antarctica mass loss over time. And they proceed at an acceleration rate of 36 gigatons per year square. So every year, on average, the mass loss from these ice sheets increases by 36 gigatons. That's about 0.1 millimeter. Right now, the ice sheets are contributing about equally as all the mountain glaciers and ice caps. Interestingly, the acceleration in mass loss from the ice sheet is 3 times bigger than the mountain glaciers and ice cap, which means that if this trend continues, the ice sheets will dominate sea level rise in the coming decades. They are operating on a much faster pace. What are some of the climate forcing? There's evidence of warming of the Southern Ocean, at least faster than the rest of the Southern Hemisphere. but very few data along the coast of Antarctica. So it's difficult to say how much of that heat is actually able to make its way to the glacier ice. There's evidence of warming in air temperature. Probably the most significant result from regional climate model reconstruction of accumulation in the Antarctic is that there's no long-term trend in precipitation. Climate models predicted an increase in precipitation over the Antarctic that we haven't seen yet. In Greenland, this is a view graph from Connie Stephan, which shows the increase in melt area over time. The total area of ice sheet melt in Greenland increased by 65% since 1979, about 2% per year. This is comparable to the rate of decrease of the sea ice extent in the summer in the Arctic. So this is a very rapid pace of change. And this is the extent of melt in 2007 over Greenland. At Swiss Camp, this is a record of temperature since the early 1990s, which was actually 1992 was a cold year, but the change in temperature in this area is 4 degrees since 1991, so a very rapid warming of 2 degrees per decade. A lot of research has been going on investigating the role of meltwater on the fast flow of these glaciers, because we know that meltwater is fundamental in the process of glacier flow. So a lot of research was aiming at determining how much of these processes influence the rapid increase in glacier flow around Greenland. And I'm not summarizing all of these studies, but the bottom line is that basal lubrication is not an effective process to explain all the glacial changes we're seeing right now. It can produce these rapid changes in ice flow over short time periods, but it does not produce significant changes in glacier flow over a longer time period, and it's not sufficient to explain some of the glacial changes we've been observing in Greenland. This is not totally surprising because in Greenland, the glaciers flow only 8 to 10% faster in the summer compared to the winter. The current line of thinking is that these glaciers have been destabilized in the frontal region, and this occurred from an ungrounding of the glaciers. The grounding line is retreating. The pinning points are not acting to resist flow, and the glaciers can accelerate, and the changes in speed can be very large. Question is, what causes ungrounding? It can be caused by surface melt, thinning from the top. It can be caused by melting from the ocean, because a lot of these glaciers end up in the ocean. It can certainly result from a loss of buttressing if an ice shelf collapses in front of the glacier. Ice-ocean interaction occur in two different flavors. On Antarctic ice shelves, there's different modes of melting of the ice, depending on whether it's coming from sea ice formation or if it's a direct inflow of warm water at intermediate depth. This water is able to reach the deeper ice, which is warmer, and also where the melting point is depressed, is increased by 0.75 degrees per kilometer. And the typical sensitivity of this process to warming is about an increase of melt of 10 meters per year per degree warming of the ocean. 10 meters per year is about 100 times the level of mass exchange at the surface. So a lot of these mass balance of these ice shelves are determined by what's happening at depth. More recently, we paid more attention to what's happening to tidewater glaciers. They don't form floating ice shelves, but they terminate in the ocean, and they interact with the ocean. The interaction is guided by a convective flow driven by subglacial discharge, which brings this buoyant plume of fresh water. The faces are vertical, so it promotes very strong conversion as opposed to the nearly horizontal shape of ice shelves. And the melt rates tend to be 10 to 100 times bigger than underneath ice shelves. What do we know about ocean warming? This is the result from Boning et al. In 2008. From the Argos data, which suggests, as Sarah Gill showed a few years earlier, that the Southern Ocean is warming. But you see that there's no data close to the periphery of Antarctica for us to say much about what's happening on ice shelves. In Greenland, David Harlan et al. Showed that using fishery data, there was a rapid warming here, shown with these red colors, of the waters at depth along the west coast of Greenland around the mid-90s. And this is when the Jakobshavn floating ice shelf started to disintegrate. And they attributed the disintegration of this glacier to the intrusion of these warm waters, which have a North Atlantic origin. I mean, they come from the tropics and are deviated by Iceland into the West and East Greenland current. I'm going to talk about that again here. In this view graph, I show results from the ECO2 reconstruction of ocean state around the Arctic. We see in this graph the warm waters from the Immiger Sea that they deviated by Iceland and go along the coast of Greenland. This is the East Greenland current. It goes around the tip of Greenland into the West Greenland current. Most of the heat goes into the Labrador Sea, but some of it makes its way up in Baffin Bay. And in the time period 93 to 2009, if you look at the ocean temperature at 200 meter 50 depth, which is the depth at which ocean water can attack the glacier ice from Greenland. Some of the most dramatic increase occurred in northwest Greenland. This is also where we see the largest increase in mass loss in Greenland. And in 2001, 2009, the ocean waters actually cooled down a little bit along southeast Greenland. Some of the warm water that intruded earlier ceased to intrude as much. And indeed, we've seen a decrease in the mass loss from these glaciers during that time period. Some of the temperature changes around the coast are pretty dramatic. We're talking about 1 to 3.5 degrees change in ocean temperature. So from this, we conclude that ocean warming is widespread around Greenland. Using some model simulation of the influence of runoff and ocean temperature on melting, we calculate that this warming of 1 to 3 degrees has had the potential to retreat this glacier front by 500 meters up to 1.5 kilometers. And we think this is the main driver for the retreat of these glaciers. Now, I have a selection of a few view graphs to illustrate some rapid changes that we've seen in ice sheets. As of today, we can't say that ice sheets are collapsing. They're changing rapidly. But we've seen some events which I think are pretty significant in terms of how fast an ice sheet can respond. This is a time series of images of the collapse of Larsen A and Larsen B, 1995 and 2002. Larsen B had been in existence for 10,000 years. It exploded literally in a period of 3 weeks in 2002. It would take centuries to reconstitute this ice shelf. The process of ice shelf collapse in the peninsula is irreversible. More importantly, we've seen the effect of the removal of this ice shelf on the glaciers upstream. The glaciers accelerated so rapidly and thinned so rapidly that they left pieces of ice stranded on the valley walls. The glaciers used to flow at 400 meters per year. They triple to their speed up to 8 times faster. Some of these glacier speed have decreased over time to only 5 times faster. But there's nothing in the system that shows that this acceleration in ice flow is subsiding. It's maintained. So basically, these glaciers are going through an irreversible collapse following the demise of the ice shelf. In West Antarctica, we are seeing the deep glacier from the marine sector of West Antarctica, which are all accelerating, widening, and accelerating in unison, thereby responding to a common forcing. And because this area is marine-based and with a bed deepening inland, there's reasons to believe that this state of retreat is unlikely to change anytime soon. Jakobshavn-Isberget has been retreating since the Little Ice Age. This is the floating extent of Jakobshavn-Isberget in Greenland. Even during the warm period of the 30s and 40s, it did not retreat that fast. It took about 50 years to retreat from that point to here. It took 5 years to retreat from here to there. There again, Jakobshavn-Isberget has been experiencing an irreversible collapse of its floating ice tongue. It would take decades to reconstitute portions of this ice tongue. In the northern part of Greenland, there are places where there were ice shelves. This is Ostenfeld Glacier, the very northern tip of Greenland. Most of this ice shelf is gone now. This is Zachary Eastrom, on the northeast sector of Greenland, with the floating extension here merging into sea ice. In 2006, most of this ice shelf also collapsed. This glacier, which doesn't even have a name in northwest Greenland, saw a collapse of about 6-7 kilometers between 2000 and 2006. Those of us who looked at this glacier thought we were mislocating our imagery, because on one image you see it, on another image it's gone. So some of these changes are pretty drastic. Now, if we put all of this in terms of sea level rise, the IPCC AR4 estimate were placing sea level rise by 2100 at about 40 centimeters or so. The semi-empirical model of Stefan Ramsdorff, which includes thermal expansion, changes in ice sheets and everything, is predicting something twice higher. Where do we stand today? Well, if we use the same rates of increase in mass loss of the ice sheets and mountain glaciers, and we assume these rates of increase in mass loss are maintained throughout the century, we are pretty much following the Stefan Ramsdorff curve, 30 centimeters by 2050, and in about a meter by 2100. But there's a possibility for ice sheets to respond faster or less fast, or maybe possibly slower. In Antarctica, the sectors that are changing in West Antarctica are expected to be vulnerable to climate change. There's another part of Antarctica, in East Antarctica, which is potentially unstable, which is largely overlooked by the research community, even though there's some indication of changes ongoing on some of these glaciers. There's more ice stored in this sector alone than all of West Antarctica. In Greenland, a lot of the glaciers that changed in the recent years in southeast Greenland, except for Jakobshavn and Isbrae, drain sectors that are grounded well above sea level, which we don't expect to respond extremely rapidly to climate forcing. The sensitive sectors in Greenland are in the north. This is all marine-based, and they have not yet responded to change. So there's a potential for more rapid change in the future. In conclusion, we've seen major progress in estimating ice sheet mass balance, mostly from satellite data and using a combination of different tools. Right now, these ice sheets are neck to neck with mountain glaciers and ice cap. They kind of caught up with the mass loss from mountain glaciers and ice cap. But their rate of acceleration in mass loss is much greater, and if this continues, and there's some reasons to believe that this rate of mass loss will continue to increase, ice sheets will dominate sea level rise. At the current rate, they would raise sea level by 30 centimeters by 2050. In terms of forcing, we find that lubrication by water is not a major driver. Thermal forcing from the ocean is probably a major driver, but there's a lot of things we don't know about how these processes occur. We don't know how warm the ocean is and how the increase in melt affects the glacier dynamics very well. Future progress is hampered by many difficulties. The lack of basic data. We don't have a lot of good data on the ocean temperature. Poor knowledge of ice thickness on the glaciers, very poor knowledge of the bathymetry in front of glaciers and underneath ice shelves. Numerical models have to catch up. They're going to take a while to catch up. We are losing some basic sets of observations. ISAT-1 is no longer operating. InSAR is terminating its mission. PALSAR is going commercial. And GRACE is going to soon terminate its mission, and there's no follow-on mission. And finally, there's the scale and complexity of the problem. I think it's very doubtful that we're going to predict what ice sheets are going to do in the future. It's probably similar to predicting earthquakes. The last bullet is probably not the least. We have to remind ourselves, even though we get familiar with all these changes in Greenland and Antarctica today, that none of these changes were predicted by models. So ice sheets, in a way, decay well ahead of predictions. And yet, many of our assessments of future changes of these ice sheets remain fairly conservative because nobody wants to be a scarecrow. But obviously, this attitude will have to change a little bit because for a lot of people that in particular are affected by sea level rise, they don't particularly care about business as usual. They just would like to know how bad it could be, right? Thank you.
So thank you, Eric. So we will keep the questions for the roundtable, and we move to the last speaker of this union session, who is Michael Gill, speaking about the future is warm but uncertain.
Thank you. Okay, so as Mark Twain pointed out, predicting is difficult, especially the future. Actually, Jim Zakros pointed out that even predicting the past sometimes is a little bit difficult because of the difficulty with the proxies. But, and of course, we had the most facts from Eric. So what I will have to say is a little bit more qualitative, a little bit more tentative. So there was already some mention of the last assessment report. And one of my points is that these assessment reports, for various reasons, including sociological and linguistic ones, have been divided into three parts. The physical science basis, which presumably is most solid, and then impact, adaptation, and vulnerability, and mitigation of climate change. So let's see, where is... okay, so here, here, and there. And as I said, the communication between these has been somewhat hampered by differences in language, you know, which sort of set up a barrier. So, you know, one of these groups was throwing over this barrier some scenarios, and the physical people caught what was thrown over and did some simulations, and then threw over the barrier back, the results of those simulations, and then they had to do something with adaptation and mitigation. And of course, this is an interactive process. We're in the midst of this interaction and trying to change how, you know, people will behave with respect to those scenarii. So basically, I will first try to talk about the $1 trillion question. You know, it used to be said that $1 million here, $1 million there, and pretty soon you're talking real money. Now it's $1 trillion here, $1 trillion there, and pretty soon you're talking real money. So global warming, when and by how much, adaptation and mitigation, when and how, you know, now or later, etc. And so the emphasis will be, on the one hand, on uncertainties, both the causes of these uncertainties and possible fixes, and then which kind of economy does warming impact. And I will try to talk about something that is not much talked about, which is the fact that the economy is also something that is not in equilibrium, but has some intrinsic variability, which economists call endogenous. Remember that, you know, barrier over there, part of the barrier is this linguistic one, okay? Endogenous is intrinsic. And then a vulnerability paradox, and again try to conclude with some generalities and draw some conclusions. So, the $1 trillion question, global warming, when and by how much, adaptation and mitigation, when and how. So quite clearly, we've been doing extremely well in, you know, spewing up greenhouse gases into the atmosphere. I mean, we've done much better than, you know, the past, the last some thousands of years. So we have to somehow cope with that. Again, this is from the last assessment report. You know, here are the greenhouse gases, and here the error bars are relatively small to the size of the change. And here are some of the aerosols which have been mentioned in connection with geoengineering. Here the error bars, especially on this one, this Indirect effect of aerosols are fairly large, but clearly the net effect is towards warming. So, you know, I was reading in today's sheet that there are three kinds of people: skeptics, contrarians, and deniers. And clearly, it's a waste of time talking to the deniers because you're not listening. The skeptics are great. I'm a skeptic. You know, I'm teaching my students that science is skepticism. You maybe have to deal with the contrarians. I don't know. Okay, so uncertainties. Again, you know, there are lots of acronyms because there are hundreds, you know. As soon as there are three people working on the same topic, you have an acronym, and here you have hundreds of people. So Assessment Report 4, Working Group 1, which is physical science, and Summary for Policymakers. Okay, so the different colors here, you've seen this before, but I will go through it very fast. So the different colors are different scenarios. And for each one of these scenarios, you know, the 20 models or so that have been run on them still have a range of uncertainties which is a few degrees. Now, of course, you know, your attitude could be, yes, all I have to say is how bad it could be. But that's not quite true because, you see, this is a big problem, but it is not the only one that humanity is facing. So, you know, it would be good to have a little bit of a reduction in this range of uncertainties. Okay, so how about that? Well, again, the assessment report has this wonderful table. The columns are different things like phenomenon and direction of trend, likelihood the trend occurred in the late 20th century, typically last 50 years or so, likelihood of a human contribution, and likelihood of future trends, etc. And so some of these are quite likely, very likely. Some of them are likely, some are even virtually certain. The one that I really love is more likely than not. Okay? I always get a laugh out of that. Thank you. Okay? So clearly probability plays a role in this, okay? Probability and statistics and stochastic processes. So uncertainties, causes and fixes. Well, there's one sensitivity that since 1963 at least, in the climate community, you know, there have been other papers, but the climate community is most used to the Ed Lorenz paper of 1963. We know about sensitivity to initial state. I'll show that on the next slide, but the one that I really want to talk about is sensitivity to model formulation and parameters. You know, Eric said that models should catch up, so let's see whether they can. Okay, so how do you deal with sensitivity to initial state? Well, you run ensembles. Okay, this is one that many of you have already seen also. It's what happened with the forecast for this huge storm, you know, around Christmas of 1999, which basically blew the roof off the office next to mine in Paris. And this is what the deterministic prediction did, and this is what the verification did. So this is the eye of the storm. And here you see an ensemble of 50 members. And actually you see that there isn't really just a funnel, you know, just an exponential divergence of trajectories, as you would think from the Lorenz 63 model. There's really a bimodality. Some of them did pretty well, and some did awfully. Okay, so there is another kind of nonlinearity, but I don't have to talk about that one. So let me talk about sensitivity to model formulation. Okay, this is called the Francis Bretherton horrendogram of Earth system science. This is the report of the NASA Advisory Council that launched not 1,000 ships, but at least launched the words Earth system science. And you know, there are lots of things happening here. There's atmospheric physics, which was pretty well developed by that time. And then there is ocean, this is ocean dynamics. The atmospheric physics was pretty well known. Ocean dynamics somewhat less, but catching up. And then marine biogeochemistry and terrestrial ecosystems and a lot of other stuff. And now people are very seriously talking not just about launching satellites to observe all of this, but also about building systems that would incorporate all these mechanisms. And so also they're talking about continuing to increase the resolution of the models, okay? One definition of a GCM, of a general, they used to be called general circulation models. Now they are called global climate models, but the acronym has stayed the same, GCM. One definition of the GCM is the biggest model you can run on your biggest computer. At the beginnings, a GCM was something that you can now run on your laptop, okay? But by that definition, you can't do an enormous amount of experiments or run them for very long. So, the idea was up till now that those uncertainties, remember the ones that we are talking about here, that these uncertainties were mostly a matter of tuning knobs. We hadn't figured out this little engineering exercise that you solve, or your little, baby solves every day in tuning the dial of the hi-fi, of the stereo system. Okay, so there are many knobs, and we're having trouble with those. But maybe there's more than that. Maybe there is actually some sort of fundamental problem with a system that complicated. Okay, and it actually turns out that this might be intrinsic rather than a mere tuning problem. And so it used to be thought that for any mathematical model, whether discretized like a GCM or continuous or what, to be interesting in physics, it would have to be something called structurally stable. In other words, precisely if you change it a little bit, if you increase the resolution or you add a few mechanisms, it should give you results which are pretty much the same. That happens not to be so. Even the Lorentz 63 model is not structurally stable, let alone these GCMs. So what can we do? Well, one thing that we might be able to do is actually to take seriously this business of stochastic parametrizations. So, it was mentioned that so far we have been sort of learning about difficulties with dynamical systems which are what's called autonomous, for which the forcings are constant in time. But that is certainly not so for climate. On the one hand, we have things like the seasonal cycle. On the other hand, we have what we are doing to climate. So we have to take into account changes in the forcing, both deterministic, like what we are doing, and stochastic, like volcanic eruptions. So it turns out that after we finally learned what a strange attractor is, namely something that is strange for constant forcing, it should be replaced by something which is called a random attractor, in which you have an evolution in time of the forcing, combining deterministic with stochastic, and you want to look at the behavior of the attractor at a fixed point in time, whether it be sometime in the past, in the present, or in the future. So in order to be able to do that, you have to pull back a little bit. In the deterministic case, the random attractor is just called the pullback attractor. When the forcing changes in time, you have to pull back a little bit and let your phase space flow to the point where you are now and observe what is going on. And so just to show you, this is the famous Lorentz attractor, but it's just a snapshot of that when I add some multiplicative stochastic forcing. So you see that it looks pretty ferocious. This one looks even better, okay? And this is actually for noise that is quite substantial. It's comparable to the signal. That forcing on the right-hand side, this alpha here in front of the multiplicative nonlinearity and the Brownian motion is 0.5. And it turns out that this stuff has interesting properties that I don't have the time to talk about, but I will tomorrow evening in the Mandelbrot memorial session of NP 1.1. Okay, so now let's go on from toy models to serious models. Okay, this is parameter dependence For something that can be called an intermediate coupled model, you know, there are actually some discretized partial differential equations in it. It's the one that was published in Science and Physica D about 15 years ago. And so the parameter dependence can be smooth or it can be rough. Okay? You see here changes in the skewness of this model's Nino 3 SST and of the kurtosis. And you see that there are, this is a range of, this is just one trajectory taken from somewhere here. There are plages, if you will, of fairly smooth dependence, and then there's some rough dependence. Okay? And so when it is smooth, it turns out that you can do, instead of just doing this haphazard tuning that people have been doing, you can do some optimal or systematic smoothing, where you take one of the many parameters of a GCM. Okay, so this is now this ICTP atmospheric GCM. It's out of a paper that just came out in PNAS last year. Okay, and these are some model runs, and you can fit them either linearly, that's the green line, or quadratically, that's the blue line. And there are certain cases in which the minimum lies within the interval within which you are smoothing. So it might be something like this, or it lies at an endpoint of the interval which you consider to be reasonable for the value of that parameter. Okay? And so these are some results for different objective functions. Okay, so this is a cloud albedo, this is a gustiness parameter, and these are, you know, precipitation, temperature at 200 millibar, zonal wind at 200, and the big sphere is the one that you get with a quadratic fit, and the small ones with a linear fit. And the trick is that you can actually do this in finite time as opposed to brute force, which would be in still finite but very large time, practically infinite wall clock time. Okay, so it turns out also that it's better to have a so-called multi-objective algorithm rather than a unique cost function, but I don't have the time to discuss that because I would like now, okay, there's one more slide on the climate side, and then I'm moving on to the economics. So again, the idea here is that let's say for AR5, you would like, sorry, let me backtrack. At the beginning of AR4, there was an idea that a lot of this spread just had to do with the fact that people wanted to play who shouldn't be in the sandbox. You know, they had lousy GCMs. And that the good GCMs would come out much closer to each other. The trouble with that is, first of all, you don't know what a good GCM is. Basically, most of them, you know, still need all sorts of flux corrections. They don't do ENSO well, they don't do this well, they don't do that well. But let's say that a good GCM is the one that has the largest computer and the largest group of people. Well, it just so turned out that two of those best GCMs came out at the opposite ends of the uncertainty range. Okay? So you have to classify your results some other way. And this is sort of the little red flecks are the different GCMs with just deterministic parameterizations. And then you start exercising stochastic parameterizations and maybe increasing the variance. And if you increase it very much, all of them are going to fall into the same cloud. But if you increase it by some moderate amount, you might find that certain GCMs fall into certain classes, and you can look at really what they have in common and what not. Okay, so which kind of economy does warming impact? Well, basically, people have been using something called IAMs, yet another acronym. How many people know what an IAM is? Okay, maybe you are too timid. An IAM is an integrated assessment model. Okay? Now, the trouble with integrated assessment models is that they assume that the economy is, roughly speaking, in equilibrium or in smooth long-term growth. Well, have you seen an equilibrium, an economy that is in equilibrium? I, unfortunately, during my lifetime, haven't. And furthermore, George Soros, who certainly knows something about economy and finance, says The currently prevailing paradigm, namely that financial markets tend towards equilibrium, you know, the invisible hand, okay, is both false and misleading. Our current troubles can be largely attributed to the fact the national financial system, and not just the financial system, has been developed on the basis of that paradigm. Essentially, the dominant school of economic modeling assumes that. So let's take a toy model of the economy called NEDIM, non-equilibrium dynamic model, which represents, again, it's a toy model, one producer, one consumer, one goods, used both to consume and invest. It is based on the model, on the long-term growth model that won Solow the Nobel Prize, in which he assumed things like demand is equal to production, okay? I mean, it was okay, and it got him the Nobel Prize, but that's not the way that things usually happen. So these kinds of equilibrium constraints were replaced by dynamic relationships that involve adjustment delays. If you remove those, the equilibrium is neoclassical and identical to this Solow. If the parameters are changing slowly, it would have the same trajectories. But because of various delays, this model dynamics exhibits Keynesian features with transient trajectory segments and response to shocks. In particular, it possesses endogenous business cycles, which the economic models that go into the IAMs don't. So, you know, it used to be that we call these things bifurcations. Now, because of the influence of a very influential book in the social sciences, they're called tipping points. So there's a change in behavior, sharp change in behavior from stable equilibrium to a limit cycle, a business cycle. The bifurcation parameter in this case is an investment coefficient, essentially something that has to do with the flexibility of investment, how fast you throw more money when you see that money is growing, okay? And this is the range of your business cycle in this case. And it looks like this, okay? It has actually rapid recessions and slow expansions, which again, those other models don't, because they're basically AR1 models. You know, they regress to the mean, invisible hand. So here's your business cycle. And so we observe this vulnerability paradox. You know, the question is, when does a disaster cause greater long-term damage to the economy, during its expansion phase or during a recession? If I didn't use the word paradox, you obviously would have told me, as leading economists would have, that it is worst during a recession. Well, let's see about that. Okay, what we're looking at here is the production in the model, and this is the production loss due to a shock. Now, you have to understand that anything, a tsunami, an earthquake, windburst, has an immediate impact. It destroys some houses and so on. And then it has a more lasting impact because it affects production after that. So I'm talking about that secondary effect. So it turns out that during a recession, this secondary effect is at a minimum, while if it happens during an expansion, it's at a maximum. Okay, so this is the vulnerability paradox. Now, of course, you might ask me, yes, but we can't, you know, we have no control over the eruption of a volcano or an earthquake. So does this matter on the average in the long term? And the answer is yes, it does. Here is a table that says what happens if there's no investment flexibility. So this is the mean GDP loss as percent of baseline GDP. This is when you have a low investment flexibility, and this is when you have a high investment flexibility. Now, the numbers might be all off, because this is a toy model. It might be tuned to all sorts of things, you know, to the EU equilibrium over the last 30 years, to disaster that impacted things, etc., out of Munich Re, but the numbers might be off. The main point is that there are economic parameters on which you can act in order to minimize the damage that nature does to the economy. Okay? So, the question isn't whether it's getting warmer. It is. Nor whether we contribute to it. We do. But it is by how much it is getting warmer and by how much do we contribute to it, because it matters for the rest. Okay? These two questions are important in terms of lives, dollars, euros, yen, whatever, renminbi. They are difficult. They involve theory, actual thinking, computations, observations, okay? And, of course, they are pressing. If not now, then when? And I'm just going to leave you with some references. Thank you very much.
Thank you very much, Michael. So I will ask the three speakers to come to the stage, and I will leave the chair to Thorsten Kiefer, who is Pager's chief officer, and he will manage the round table. Oops.
Oh, this works that fine. No, I don't need to. That's fine. Okay. So thank you to all three speakers. So as Danny said, I'm Thorsten Kiefer. I'm from the PAGES project, Past Global Changes project, and I'm here to represent the International Geosphere Biosphere Program. That's our umbrella organization. And IGBP, as it's also called, was and still is instrumental in launching this debate about the planet under pressure, and also to organize, set up this conference that will happen in less than a year from now in March 2012 in London. If you're interested in global change science and the broader context of it, then this might be a good event for you to attend. So with that, I invite you to ask your questions to the panelists, or to comment with a comment that leads into a question or a hypothesis that can be discussed by the panelists.
A little questions, maybe a little comments. My question don't need answer. The first question. In principle, planet is under pressure, but maybe we are under pressure of mistakes. The first question, why does we consider the term greenhouse effect? Because the process in greenhouses are absolutely different from the process taking place in atmosphere. Because in greenhouses, glass prevent convection, and in atmosphere, pseudo-greenhouses gases prevent infrared radiation. It is the first question. And maybe comments. The second, why we miss the effect of dirt greenhouse? Because human activity produced more both gases and dust. And gases increase temperature, dust decrease temperature. And according to our say, the second effect is more significant. This is my question. A little comments more. You and the second reporter used data of short monitoring and extrapolated for a long time. But we are under control a number of factors, abiotical, biotical, and social one. And for prediction, we need use the more long monitoring, because abiotical factors are stronger than biotical, biotical are stronger than social factors. Human activity is not so significant as natural factors. And we are under control of cyclical process. For example, one hurricane has more energy than
I'm sorry, really, could you ask questions so that we can get the discussion going?
Thank you.
Can you repeat your question, or was it not?
The question, greenhouses effect, this is first question. And the second question is effect of dirt greenhouse.
So, is someone ready to, Michael?
Look, I did mention, you know, in one of my slides, I did show both things that have that increase the surface air temperature and those that decrease it. I mean greenhouse gases and aerosols. If I understood your question correctly, because it ran for a long time, your question is, well, we're doing both things. As I mentioned already, it has been suggested that we could just spew more aerosols into the atmosphere and, control things to the right temperature. Well, again, this is a big debate, and the various learned societies have been looking at it, but let me put it sort of my own perspective to it. See, we are already conducting an experiment with our planet. We're heating it up. It's not clear exactly by how much and when and so on, but we're heating it up. But that we're doing because we sort of don't have a choice, or think we don't have a choice, or we didn't have a choice. We wanted to live better and so on, and it costs CO2 and methane and so on. Well, the idea that you would do a deliberate experiment, not because you can't help it, but because you feel like it, without having somewhat more certainty about understanding a little bit better how the system works, is not one that I at least find particularly appealing. The second question I didn't understand.
Any other questions from the audience? Oh, André. We can always count on you.
Okay, thank you. That's probably related to what Michael said. Michael, can you comment upon the possible uncertainties in weather forecast and the possible uncertainties in climate forecast?
Well, thank you, André, for the lovely question. One of the questions is, well, if you can't forecast the weather for tomorrow, or maybe you can forecast the weather for tomorrow, but not for next week with great accuracy, how in the world can you say much about the climate tens of years from now? Well, there's one short answer which says that you can't. There's a slightly longer answer which says, which I once read from a French journalist who has been around climate people for a long time, but he clearly has been talking to the wrong one, because there was something about having, that climate has nothing to do with the uncertainties of weather prediction. It's a heat bath and whatnot. That's silly. Simply the times, the engineers say one person's signal is another person's noise. For the weather forecaster in Washington or Toulouse or Exeter or whatever, the signal is the weather, tomorrow's weather. For the climate person who's trying to look at decades, that's the noise. And that's exactly what I was trying to talk about in the part of the talk that dealt with so-called random dynamical systems. The same issues about the behavior of a dynamical system apply to both. We just have known the climate system we have thought about it systematically for a shorter time than about weather. And there is also the difference that the weather is verified every day, okay? Every day you know whether you took your umbrella and it didn't rain, or you didn't and it did rain. But not every day are you going to be there 10 years from now to tell whether your model told the climate correctly or not. So in many ways, the climate is not in equilibrium any more than, the economy is in equilibrium. It is driven by a dynamical system, and we don't understand that dynamical system perfectly. But if we can forecast the weather for a few days, we should be able to forecast the climate for at least a few years, which we don't yet, and eventually for a few decades.
Any
Give
other
a question to the other speakers, please.
Yeah.
It will be a short question about ice. Eric, you said in your conclusion that the thermal effect from the ocean is something clearly important. but we don't understand well it. Is it not a slight contradiction between these two assertions?
Well, because there's, we don't understand the effect of the ocean very well. We understand the basic physics. It's no surprise that the ocean has a big impact on ice sheets, and in fact, all the models have been developed in the past, even with large simplifications, always acknowledge that the most efficient way to collapse an ice sheet is to warm up the ocean. This has not been used a lot in ice sheet prediction because we don't know how the ocean is going to warm up, especially along the coastal sectors of ice sheets. And we don't know how the melting of ice is going to respond to that warming. It involves more than just the heat, but the circulation of ocean waters in front of these glaciers or underneath the floating ice shelves. And then even if we figure out this part, we still have to figure out how the ice dynamics is going to respond to this massive ablation of ice at the front. What is the spatial pattern of mass loss? Is it from the bottom, from the middle? Is it proceeding seasonally or from year to year? There's a lot of unknowns because we haven't really looked at that at this level of details. I think we're at the point now where we're saying, not only this is important, if we want to figure out what ice sheets are going to do, we have to have a much better understanding of these processes. We don't have good data in the ocean fjords. In the fjords of Greenland, nobody's collecting data on temperature of the ocean, on salinity. There's no data on bathymetry. If you navigate the fjords of Greenland, you're not going to find the depth of these fjords on a nautical chart. There's nothing. And similarly, I've shown on these view graphs that even though we have some good data on ocean temperature for the global oceans, we're lacking this data right around the periphery of ice sheets where we need them the most to predict what the ice is going to do. So we understand the basic physics, but in terms of observations and basic data, we are with a big question mark, a big cloud.
Yeah.
A question for Jim Zakos. Can you compare the rate of change during the PETM with what's going on today?
Yeah, obviously we've worked very hard to try to constrain how fast that carbon was released. And so we have a number of methods that we're using. We have orbital constraints, but a lot of our sections are condensed. And then we're looking at the accumulation rate of extraterrestrial helium in a lot of these sections, the assumption being that that's a constant flux parameter. And given what we've seen in a range of depositional environments, we think that the entire event from the onset to the peak excursion may last between 10 and 20,000 years. But there seems to be at least 2 rapid pulses of carbon input, and those can be occurring over thousands of years. So in general, the release of carbon is much slower than we're seeing now, at least an order of magnitude slower. And so, yeah, what's happening now is completely unprecedented, at least from what we know of the geologic record. And where it's important, obviously, with the climate system are the transient effects, but with ocean acidification. So the pH changes in the surface ocean with that event aren't as extreme as we're seeing at present and into the future. So.
Any other questions? John.
Thank you. First of all, I'm not a climate skeptic at all, but I am going to ask you a question. That if I were a member of the public, the general public, sitting here, listening to you, I mean, you're all saying, and I agree with you, we don't know, we're not sure, etc., etc. What should you be saying to reassure the public that we are doing the right things to solve some of these problems that are putting our planet under pressure?
Well, again, I would like to emphasize that I disagree with confusing skepticism with contrarianism or denialism. I am a skeptic myself, and I teach my students to be skeptics. You know, skepticism, healthy skepticism, is an essential ingredient of science. You know, I think it's an abuse of a certain part of the community to designate anybody who doesn't, you know, sing in the choir as being a skeptic. Now, as part of the general public, it is difficult to say things in the appropriate way, okay? I mean, all these concepts, see, I try, for instance, to point out to people that climate models used in the successive IPCC assessment reports are a heck of a lot better grounded in fact and theory than economic models that economic leaders listen to very attentively. You know, there are principles like energy conservation and stuff like that, which you don't quite have. You know, in economy you have theories. You have much fewer facts. So both in terms of the nature of the observations, you see, when I started becoming interested in modeling economics because I wasn't too happy with those IAMs, I realized, for instance, that there isn't a history of capital over the 20th century. Okay, you try to look for data, you know, there are data on GDP. I mean, the best database for macroeconomics is the one of the US Bureau of Economic Analysis, which goes back to about, you know, about a little over 50, somewhat under 60 years, and which contains several indicators, but capital is not one of them. What would have Marx said? You know, they didn't pay attention, okay? So, you know, there is a vast amount of data, proxy, satellite, you know, I've worked on all of those things. They are fraught with uncertainties, but there's a heck of a lot of data and theory and modeling that, you know, consistently points to the sense of the change. I say the fact, I think that there is a problem with certain colleagues overstating either the extreme character of the change or the exclusive impact of the change. You know, it is one of the major problems that we and our children and their children will face. And we better face it now. That's all I can say.
Should we ask Eric and Jim also for their strategy, communicating the results to the public, including the uncertainties? Do you have an opinion as well that you want to share?
I think you were asking if we can say that we're doing the right thing. I would ask you, do we do anything? I think, at least right now, in terms of the polar regions, we are observing the experiment. In terms of reducing carbon emissions, you can say that since the Kyoto Protocol have been signed, we've been tightening our belt, and carbon emissions have been increasing by a factor 3. So I don't see exactly what we're doing here. But I agree with the previous comment that it's about time to do something.
Yeah, from a past perspective, what we're doing looks very dangerous. And I say that because in the past, at least, where we have some sense of how these things get played out over geologic timescales, the effects or the impacts are long-term. They're not temporary. They last for thousands of years, and we know that now quite well from the geologic past. And the other issue is simply that in at least several of these cases where the rate of change is fast, it looks like the climate system goes into a transient state, as if there are feedbacks operating to accelerate and amplify the change. And so it doesn't happen that often, but we have evidence of it happening in the past. And so the simple lesson is that you don't want to change the boundary conditions on the climate system quickly or by a lot. And so, and again, this is just a sense that you get from looking at the past, the Earth's history, and so.
I think one more question, quick one. Oh, okay, in the back there. And then we should wrap up.
Hi, more or less on the same tone. Shouldn't price reflect changes in climate as well? Price, for instance, of insurance, like covering property for hurricanes or things like that. What I see in my experience working for a company that does model for insurances is that people are not ready to accept any change in the near future, and that at the same time they're very sensible to any change in price of things, which in a sense can convey some information about what's going on. So my question could be, what do you think the climate science could have a role in helping people understanding what are likely to be effects on their own life in the near future, like 3 to 5 years also?
Look, to the extent that we believe people who have made a lot of money, you know, this is taken quite seriously by the insurance and reinsurance industry and by various other industries, you know. In the same way that weather derivatives have been so, you know, played an important role on the Chicago Mercantile Exchange for quite a while. There's talk about doing things like this for climate. So, you know, people who really, well, I should say, those who unfortunately really matter take this quite seriously, okay? Maybe, you know, the general member of the public doesn't or only takes it half seriously. You know, some of my social scientist colleagues have taught me about the way that you should take polls. You know, it turns out that there are lots of people who will tell you, oh yes, you know, I'll do this and I'll do that to prevent climate change. So you slip in a little question about, you know, will you buy the new Sigma-Jig 17, which will do this or that? And the person who ticks that one off is suspect with respect to the answers to, you know, his or her attitude with respect to everything else. So I think that, you know, this is happening. I mean, collective consciousness of, you know, people might not be willing to make big sacrifices and belt tightenings right now, but I think that the consciousness is creeping in.
Okay, thank you. And thank you is the word of the hour now, so thank everyone for attending, listening, for those especially who seeded the discussion with their questions. And of course the three speakers and Denis Didier also for pulling off this session. So thank you very much.